share screen. Okay. All right, let's go ahead and get started. So today we have another lesson, another set of notes we're going to do. Due today is the chapter 6 opener. Okay, so there wasn't a work paper for the chapter 6 opener, so I'm just trusting that you got it done. I'll check it on Big Ideas. Also, yesterday's 6.1 homework, no work paper for it. Most of them were just, is this a function, yes or no? So I don't need you writing a bunch of yeses and nos down on your paper. You will need a work paper for this 6.2 and tomorrow's 6.3. If nothing else, I mean, there's some problems on this homework where you'll have to plug some values in, plug in for X, find a Y, and they're also going to have you write functions. So yeah, there may not be a whole lot of work, but like writing the function down is the work. And so I want to see those answers on your work papers. So let's look at, this is 6.2. If you have not downloaded these notes, they're blank right now on Google Classroom. You can download them and fill them in with me. Of course, when you guys watch this video, they'll be filled in and you can watch the video and follow along in the notes that are already filled in. Dylan.
Will we be going to the lunchroom tomorrow after like at the end of the day?
For pause award, maybe. Yes.
Are we able to just listen and then download the later notes? Or do you want to?
If you're in class, I want you following along. It's been proven that you're more likely to retain the material if you're if you're actually writing some of it down and doing it versus just watching. Because even though a lot of people are visual and some are audio learners, a lot of people learn hands-on, and so. Even if you didn't get it, you could always go back through the notes on your own afterwards. So let's look at the first two examples. They want us to complete the mapping diagram. Of course, we talked about mapping diagrams yesterday when we talked about functions. It says complete them for the area of each figure and then write an equation that describes the function. Now, yesterday's lesson was, is this a function or not? All of these examples from today's notes will be functions. They're going to want us to write those functions. Okay, so they're going to give us mapping diagrams, they'll give us a graph, they'll give us a chart, they'll give us just some points, and they're going to ask us to write the functions. Some of them be linear, some of them be nonlinear, but that still makes them a function. Now, yesterday's lesson I know was a little confusing, so if you haven't finished 6.1, before I start this example, maybe I might want to reference this real quick. If you're looking at a mapping diagram and you see that an X value has 2 arrows coming out of it, that's bad. That's not a function. Because when I plug in an X, I'm only supposed to get 1 Y. Okay? I'm supposed to get 1 number, not 2 different numbers. I can't have that. However, if you saw that instead of each arrow going across, maybe this 2 went here, that's actually okay. Let me give you an example of a function that would do that. When I plug in 1 for X, what's 1 squared? I get 1 for Y. When I plug in -1 for X, what's -1 squared?
1.
I get 1 for Y. So what I have here, if you're, they're thinking, this might not be a function. It is a function, because on a mapping diagram, this is what it would look like. And each X value still just has 1 arrow coming out of it. Yeah, it's pointing to the same number. That's okay. Okay, still a function though. What I can't have is multiple arrows coming out of the same input or the same X. So that's kind of, in summary, what we talked about. And if that's still confusing you, come talk to me during success time and I can maybe give you some more examples that will clear that up. We also talked about the vertical line test. So when they give you a mapping diagram, you can tell that way looking at the arrows, but if they give you just a graph of something, the vertical line test says that if you draw a vertical line anywhere through that graph and it crosses your function more than 1 time, that's a problem. That means that you got 1 X going to 2 different Y's, and that's not okay. Olivia?
Well, the vertical line test, will that be on any of our quizzes?
It could be. It could be. Okay. Or it could be in IXL. It could make its way on as a bonus, or it could make its way onto the test later. Okay, so just because it's not on Tuesday's quiz next week doesn't mean that it won't be on a test eventually. Okay. All right, so for example A, it says complete the mapping diagram and then write an equation that represents the function. So we have here a triangle. We have the base of this triangle being, well, what's 2 plus 2? 4. So whole thing's just 4. And the input is the x. So they're telling us to plug 1, 2, 3, and 4 in for the height of this triangle. And then the output is the capital A, and that stands for the area. So the area formula for a triangle is what, Dylan?
A equals B times base times height divided by 2.
Sure. Yep. Base times height divided by 2, or 1/2 BH, a couple different ways you could write it. That's how you find the area of a triangle. So we know that the base is 4, so it's 2 plus 2. They're giving us a different number to plug in each time for the height. Okay, so what's 4 times 1 divided by 2?
2.
Okay. What's 4 times 2 divided by 2? What's 4 times 3
12.
divided by 2? Okay, are you seeing the pattern? What's the last one going to be?
A.
Yeah. And so now that we have it filled in, they want us to write an equation for this. All right. Well, let's take this equation and let's modify it so that it's in slope-intercept form. The base was always 4. The height that we were plugging in was x, and we had to divide it by 2. So what's 4 divided by 2? So a or y, if I wrote the equation maybe like y in slope-intercept form, y equals 2x. Capital A equals 2x would be fine as well. There's slope-intercept form. So that means it's going to go through the origin, right? If I plugged in 0 for x, my whole area is 0. So the triangle is not a triangle anymore because it's not height. And then, yeah, you can even see because it's increasing by 2, that's our rate of change. That's our slope. So that just makes good sense there. Now, the triangle formula is one thing. What about the trapezoid formula? Devin, I think weren't you the trapezoid guy every time earlier this year? Probably. What is it?
Base 1 plus base 2 times the height.
You're missing one thing.
Divided by 2.
Yes, or I usually put a half, or all divided by 2. That's fine. Just like Dylan said, all divided by 2 for the triangle. So the way I remember the trapezoid formula is it's just like the triangle formula. It's almost identical. The triangle formula is 1/2 times base times height, and the trapezoid formula is 1/2 times bases times height. Like you have to add the 2 bases together. There's 2 of them in a trapezoid versus only having 1 in a triangle. So my bases are x and 2x, so 3x. My height is 2. We could actually write the equation before we even do the mapping diagram. Right, you guys see how we get the 3x? Plugged in x for base 1 and 2x for base 2, and x and 2x makes 3x. And then everything else we just copied down, except we plugged in 2 for the height of this trapezoid. What's 1/2 of 2? 1.
So it's just 3x.
It literally is just a equals 3x. So for this trapezoid, and only this one, whatever x I'm inputting, you just have to times it by 3. So the slope's 3. So a equals 3x or y equals 3x if you want to write it in slope-intercept form. So when I plug in 1 times 3 is 3, 2 times 3 is 3 times 3 is 4 times 3 is, okay, and we have our slope-intercept equation, y equals 3x. It's linear. And of course, it goes through the origin because the b value is not written, so it's a 0. Yeah, I can't plug in 0 for x because if I plug in 0 for x, that means it doesn't have any bases. So it's not a shape anymore. So the area would be 0 if I did that. Okay, that was kind of, we had some problems like that yesterday. So I think that was more just a little bit of a review I threw in here. Okay, let's talk about what a function rule is. A function rule is an equation like the slope-intercept equation, for example, that we just used, that describes the relation between the inputs, which is the independent variable, and the outputs, which is the dependent variable. Change that to blue. Match the definitions with the colors. Raise your hand if you know which variable the independent variable is. Levi? The X variable. So when it says inputs, we're talking about the X, and that makes the outputs the Y variable. And the reason that the input is the X is usually when I plug in a number, just like you guys did in the last two problems, we plugged in numbers for X, we inputted them for X, they outputted an answer for Y. The area of the trapezoid depended on what I plugged in for X. So the Y variable is always the dependent variable, whereas the one I'm already given is the independent variable. So the X that I'm usually given, that's the independent variable. So just like you guys did on your chapter 6 opener, you're going to have some homework problems tonight where they may ask you to input a number for X and it spits out a Y. Okay. I always thought of this like the, I don't know if this is still a thing. Is Call of Duty Nazi Zombies still a thing?
Yes.
Do they still have the Pack-a-Punch machine?
Yes.
That's kind of what I thought with this. Okay. The Pack-a-Punch machine, I'm losing half my audience. I'm sorry if you've never played Call of Duty Nazi Zombies before, but they've got this little machine in different maps, it's in different spots, but you put one of these regular weapons in it and it like upgrades it, right? And so, but you always knew, like if you put in this weapon, it was always going to upgrade it and give you that same weapon back. So even the Pack-a-Punch machine followed the function rule. I'm not going to put in a shotgun one time and it gives me a ray gun, and then I put a shotgun a different time and it gives me something else. So it's always going to give me the upgraded version of the shotgun. At least it did when I played. I don't know what it does now. Maybe is it random now? No, that's what I thought. So it still follows the function rule. So I plug in something, I input my X, and it's going to output a Y. And yeah, it's going to do some stuff, right? In this one, it's going to times it by 3. Maybe sometimes it times it by 3 and adds 6 to it or subtracts 4 from it, but it's going to output a Y. Madison?
Didn't you also compare the one Dr. Seuss where they have the stars on them? No. Only Pack-a-Punch.
No, it only.
What Dr. Seuss story is it?
I don't remember, but they looked at the machine, they walked the stars off and put them on. Oh, like it's recreating or making different friends.
The only thing coming to my mind right now is Cat in the Hat. When the things make a mess of the house and he brings like this machine and cleans up. What is she talking about? What story?
So, you know, like, I think, these little, like, creature things, they go into, like, this big machine, one fish, two fish, red fish.
Okay, I'll look it up later. I will try to broaden the Sneetches.
Yeah.
I haven't read it. I will broaden my horizons and use better examples next time. Levi?
You know, there reminds me more than anything for me, like a movie projector, you put in the tape and then it projects out a movie.
I like that.
Looks like
Right? You put a CD or DVD or a VC tape in and it projects, it outputs. Even computers have inputs and outputs, don't they? Like for those of you good with electronics, right?
Yeah.
Okay. Olivia?
a toaster, you put bread in,
And it brings toasted bread out. And I put a bagel in and it spits out a toasted bagel. All right. So the main part about today's lesson is writing these functions. And guys, if this is important, you need to hear me say this for your quiz Tuesday. If it can be written in slope-intercept form, it must be. So what I mean by that is if it's a linear function, write it in slope-intercept form. If it's non-linear, then obviously you wouldn't be able to because slope-intercept form is just for lines. Okay, but if it's a line like this one, I need to write it in slope-intercept form. When it says the output, what variable is it referring to? Y. What does the word is mean in math, Dylan?
Equals.
Equals. So the output, the Y equals 5 less than the input. How do I write it? Go ahead.
X minus 5.
Yes. X minus 5. X being the input, 5 less than that. That is very different from writing this. And that's wrong. that means you're taking x away from 5. It didn't say to do that. It said take 5 away from x, 5 less from x. So the way that I write subtraction matters. Plus, you write it in slope-intercept form anyways, right? So this would be y equals 1x minus 5. Your slope would be 1. Your y-intercept would be -5. But I don't have to graph this. So I'm just going to leave it just like that. Yeah, Levi?
So if there happened to be a case where it said that the output, or like x is 5 is, or well, if it was 5 minus x, would that mean that it was not a line?
It means I'd have to no. It would still would be. So this, just so we're clear, this is not the answer to this problem. But if let's say that's how they wanted me to write it, that's how it was worded. To write it in slope-intercept form, I would then move this over here, that over there, and make this y equals -x plus 5. Oops, -x plus 5. Okay, so I still could write it in slope-intercept form. Okay, but that's not what they wanted me to do for this one because it was already x minus 5. Yeah, so you just do that. Okay. Example B, the output is the square of the input. Devin, what's it going to say?
Y equals x squared.
Yep. Is that linear?
Yes. No, not.
Why? What's different about this equation that none of the slope-intercept equations have?
It's times it by itself.
Yeah. Yeah. When you write it in slope-intercept form, the exponent, the x exponent is always a 1. Or heck, sometimes it's not even there. Sometimes like the function might just be like y equals 6 and it's a horizontal line where the x variable is actually a 0 now. It cancels it out. If it's 2 or more, it's going to curve. The x is going to curve, and so this would be non-linear. And you're right, that is the function. It is still a function, it's just not a line. You'll explore it more next year. Example C, the output is 8 less than twice the input. Mason?
Y equals 2x minus 8.
Got it. Y equals 2x minus 8, and not the other way around. When it says 8 less than, that means you're taking 8 away from something. We'll start with the something. What are you taking 8 away from? 2x. So y equals 2x minus 8. Okay. We got to be smarter than just writing the numbers and letters down in the order they appear. Sometimes the order they appear isn't how it wants you to write it. 8's being subtracted from twice the x, 2x. Okay. Okay, we're not going to work with a partner, but I do like this example. It says make a table. We'll do our best to make a table. We'll make something else that shows the pattern for the area where the input is the figure number and the output is the actual area. And now it's reminding you that literally if you see 1 square, it represents an area of 1 unit, 1 square unit. Okay. So they want us to make a table or maybe a list of x being the figure number and y being the area, how many cubes or how many squares there are. So in figure 1, what's my area? 1 square. In figure 2, what's my area? How many squares are there in figure 2? 3. In figure 3, so the figure number is my x, my input, and the output is 5. Do you see what they're doing? Like each time they're adding 2 squares to the diagonal. And then for figure number 4, there's 7 squares. Question. I feel like Dwight Schrute when I say that. From The Office. Again, I'm just losing people left and right, possibly. Okay, I'm gonna write these up here. Hang on a second. Sorry, I'm trying to move these where they're all in the same row without moving them. Okay, question. Every time I increase the x by 1, is it increasing the y by the same amount? No, the question was not for you. Nothing.
Wait, who's that?
No, Siri.
Oh. Wait, are you hiding on purpose?
All right. Yes, there's someone under my desk that does all my calculations for me. All right, let me rephrase it because a lot of you gave me the wrong answer. When x increases by 1, is the y increasing by the same amount?
No. Yes.
Yes. What amount is it increasing by? 2. And is that the same? Is it always increasing by 2?
Yeah.
So this, it has a constant rate of change. Okay. 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 You're right. 2 is not 1. I wasn't asking you if it also increased by 1. I was asking you if it also increased by the same amount. Every time the x increased by 1, the y was increasing by 2. Does that make this function linear if it has a constant rate of change? Yes. The slope is always the same. When y increases by 2, that's the rise, right? With the change in y on top, the x is increasing by 1. And so this is going to have a slope of 2. Okay, so if I had to write an equation for this, y equals 2x. Okay, let me go back in time. This is where this one gets tricky. If I decrease this by 1 to get 0, I have to decrease this by 2 to get -1. It actually would have a y-intercept value of -1. Now, that's where this breaks down because although the function is mostly linear, it's not linear to start with. Because to say that I just go down 1 and down 2 for the y puts me at -1, you can't have a negative area. And so, yeah, if you were thinking, shouldn't it just be 0? It is to start with. But theoretically, it actually starts at -1 if I were to draw it straight. It starts out with 0, and then it becomes linear after that. Okay, so that's what it would be. I'm going to erase the equation because I don't think it even asked us. It just said, write an equation that describes the function. Oh, no, it did say that. So, I need to leave the y equals 2x up there then. All right, example B. Use a different color. In figure 1, what is the area? 1. In figure 2, what is the area?
4.
Okay. So far, if this was linear, right, because it's always got to be the same. When x increases by 1, y increases by 3. Rise 3, run 1, that's a slope of 3. Let's see if that continues on here. In figure 3, what is the area? Ooh, okay, hold on. It went from 1 to 4, it jumped up 3, and then it went from 4 to 9, it jumped up 5. This is not a constant rate of change. This is non-linear, but I can still write an equation for it, and I'll get there in just a second. Let's go ahead and finish the last one. Maybe this might help some of you. In figure 4, what is the area?
16.
Okay. All right. So here's your job. I need an equation of that function. What's happening to the y value each time? Caroline?
It's the x value multiplied by itself.
Yes, you're exactly right. The x value multiplied by itself. This is the function y equals x squared, the same one that Devin said earlier when it said the square of the input. 1 squared is 1. 2 squared is 4. 3 squared is 9. They're just taking the x and they're squaring it. What's interesting though is all the perfect squares, like 1, 4, 9, 16, it's your first 4 perfect squares. They increase by different amounts, but the amount that they increase by actually always goes up by the same. So here's what I mean by that. This went up by 3. This went up by 5. This went up by 7. What's the next perfect square? 25. 16 to 25 goes up by 9. So the difference between perfect squares is actually all the odd numbers. It just goes up by 2 each time. Difference of 1 and 3 and 5, 7. Not that you need to know that. It's still not linear. But it's kind of cool, I think. For what? Yeah. It's like a linear function inside of a nonlinear function. That's a good way of putting it, Levi. Just blew my mind. I don't even know what I'm saying anymore. Is that even, I don't know, never mind. Ugh, man, okay. Now, on your work papers for homework questions like this, I need you to show something. You need to show some work here. So let's say I get a problem like this. I think, Devin, did you ask me about one like this?
Yeah.
Okay. Devin said, when I write this on my paper, do I need to write that I'm plugging the 3 in for x in parentheses? Or can I just write y equals 6 plus 5? And I said, if you just want to jump to y equals 6 plus 5, that's fine. What you can't jump to is y equals 11. That's too many steps that you're doing at the same time. You need to, if you don't want to show me where you're plugging it in at, I mean, I get it. I know where you're plugging it in, and you just want to say that was 6 plus 5, that's fine. But minimum, you need to show me this work right there. Because as these get more complicated, and they eventually will, like maybe later this year or next year, if you're just used to putting answers down, I don't know where your mistake was if you got it wrong. So I need to see something so I can at least catch, maybe give you partial credit if you accidentally made a mistake.
Hunter Steiner, Jackson Brandenburg, Ethan Moore, and Madison Hunt. Please come to the office. Madison Hunt, Ethan Moore, Jackson Brandenburg, and Hunter Steiner.
Okay, we need to talk about this function. This is a bit odd. Okay, here's why this is a little bit odd. When you square a number, it's always positive. It's always going to be positive. Because think, if the number you're squaring was already positive, a positive times a positive is a positive. If the number you were squaring was negative, a negative times a negative is positive. The exception is 0. 0 squared 0. It's neither one. Okay, so maybe I should say that when you square a number, it's never negative. Maybe that fits. Okay, but they throw a negative in here before the x. So when I plug in -1 for x, this is actually what it looks like. And this is where the parentheses that when you use parentheses when you plug it in, this is where this might actually help you. This is what it would look like. What's -1 squared?
1.
Okay, now make it negative.
-1.
Okay. So it doesn't break the rules, but the exponent can't affect the sign there. I mean, that's not its fault. There's a -1 being multiplied to the x squared. So if you always square a number and it's always positive, okay, well, if you take a positive number and times it by a -1, it's always going to go negative there. So this negative in front of the x actually makes all these answers negative. Well, I'm only plugging in one number, but if didn't matter what number I plug in, if it's -1, +6, 12, -14, doesn't matter. It's always going to give me a negative answer here because that negative is sticking out in front of the x. And so what this actually looks like, remember we said that the x squared functions are parabolas? I drew you what a parabola looks like, okay? Because this one's got a negative in front of it, it's actually going to shift it and make it go the other way. Just like if I put if I have a line that says 2x plus 5, and then I say -2x is the slope, it changes the direction of the line, if it's positive slope versus negative slope. Changing this from positive x squared to negative x squared changes the direction of the parabola too. So that's what it would look like. But again, we're talking about linear functions this year. That's just added information for next year's class. Function rules can also be written f of x, which is read f of x. Okay, so the x is the input, and the f of x is the output, also known as what variable?
Y.
The y. I don't think in your textbook this year they even write f of x, but it'll be all over your textbook next year. So I'm going to introduce it to you right now. If you see f of x, that f parentheses x parentheses is just a fancy way of writing the letter y. Okay. Here's why people write function. Well, first of all, the f stands for function. The number in parentheses is what you're inputting into the function. Okay, so x in this case. The reason people write it like this is because when you plug in 5 for this problem, just like we plugged in the ones above, you can actually write it like this. Instead of saying f of x, you would say f of 5. And that means every place there was an x, you're inputting a 5 right there. It tells you what you're inputting. So as you guys get into more advanced math and people start checking your work and saying, okay, I need to see what you're inputting each time. When you write f of 5, they know you're inputting 5. And so then you would do 7 or equals 7 minus 3 and then plug in a 5. George, what's 3 times 5? 15. Okay. And Jocelyn, what's 7 minus 15? Okay. So then f of 5 equals -8. And it's like the coordinate point right there. When I plug in 5 for x, I get -8. 5 -8's on my function. What about if I plug in -2 for this function? F of -2. This is literally, that tells you, instead of writing out this, if they write it like this, they're just telling you that's what gets plugged in. That way they don't have to write this anymore. That just means plug in -2 every place you saw an x. Okay, they want you to plug in -2 for x. So f of -2 means -3 times -2 cubed plus, ran out of room, -2 squared. Now, you heard me say that every time you square a number, it's always positive. So what's -2 squared? Yeah, -2 times -2 is positive 4. It's not true about cubing a number, though. Cubes alternate back and forth. So what's a positive times a positive times a positive? Positive. There were no negatives. What's a negative times a negative times a negative? So cubes will alternate back and forth. That is because when you cube a number, the exponent is odd. If you have an odd number of negative signs, your answer will be negative. If you have an even number of negative signs, your answer is positive. That's why squares are positive. If you take a number to the 4th power, it's always positive. To the 6th power, it's always positive. But for the cubes, I can't say they're always negative. That's not true. But they alternate back and forth. Sometimes positive, sometimes negative, depending on what you plug in. So -2 times -2 times -2 is what? -8. Yes, -8, because there's 3 negatives there. Now take that -8 and times it by -3, and now it reverts back to positive. And what's 24 plus 4? So f of -2 is 28, which means the coordinate point -2, 28, it's on that function. Is that function linear? Nope. It has an x exponent higher than 1, doesn't it? It has actually 2 of them. Okay. It's going to curve. It's going to be curvy. Okay. If you've got an x exponent other than just 1, so there's actually a number up there, because if it's an exponent of 1, they just write x. They don't actually write it up there. But if it's squared or cubed or to the 4th or blah, 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 it's going to be nonlinear. It's just going to start curving around. You don't need to know what it looks like. You just need to know that it's nonlinear. Functions can also be represented by an input-output table, which is a fancy way of saying a t-table, like the ones we looked at yesterday, where they list the x's on one side and the y's on the other side. Okay? And then they graph it. And they want us to write the slope-intercept form of this function. So when I'm writing the slope-intercept form of a function, it's a lot easier to look at a graph and write it than it is a chart. So let's just look at the graph. What's the slope of that line? It rises 1, it runs 1, slopes 1. Where does it cross the y-axis at? So y equals 1x. Or sorry, I've already got the f of x, that's my y. So y equals f of x equals 1x plus 2. If they don't give you the graph, could you still do it? If this was not given to you and they just gave you the t-table, yeah, you could. What's my y increasing by each time? That goes on top, that's my rise. What's my x increasing by each time? That goes on bottom, 1 over 1's 1. It doesn't give me the x value being 0, does it? The y-intercept is always the value when x is 0, because you're right there on the y-axis. You haven't moved left to right at all, okay? So if I back this up 1, subtract 1, that's going to give me my y-intercept of 2. So I can still find it. Okay, I'm supposed to graph each function, and I'm going to use the color they gave me for each one of these. So I'm supposed to graph negative 2x plus 1. Now, is that a linear function? It is linear. It's in slope-intercept form, isn't it? Okay, so what's the y-intercept on that function? Ooh, that's really hard to see. Let's change that. Yes, thank you, Devin. This one's linear. The y-intercept is 1. And the slope is what, Olivia?
-2.
Good. So down 2 over 1. I like graphing lines. Did this in our systems of equations chapter, did it in the chapter before that. This is my linear function of y, or f of x, equals negative 2x plus 1. Okay, so that's that function. It's linear. How about the next one? Is it going to be linear? No, because it's got x squared. And so how in the world am I supposed to figure out what it's going to look like? Well, maybe we should plug in some values for x and plug in some value and get some values for y, and we can actually see what every time we input a number, we can see what it outputs. So a really easy number to input is 0. What's 0 squared? Make it negative. So 0 plus 1. So when I plugged in 0 for x, it outputted the number 1. So I know that it's going to go through that point there. Let's skip ahead. Let's input 2. If I input 2, what's 2 squared? Make it negative. Negative 4 plus 1. Negative 3. So 2 negative 3. It's linear to me. That's the problem, right? No, not linear. You said it wasn't linear, so maybe we should do another point. What if we plug in 6? Oh, that's going to give us too high. I got to pick a smaller number. What if we plug in? Let's just do the next one. Let's plug in 3. What's 3 squared? Make it negative. Negative 9 plus 1. So when I plug in 3, I didn't even know my graph anymore. Yeah, I get negative 8, and that's going to be down, we'll say right there. Not linear. It actually starts to curve. I guarantee if we plug in the opposite of these x values, we'll end up getting the same inputs, because this is going to end up being a parabola, and parabolas are symmetrical. So if I plug in negative 2, what's negative 2 squared? I'm concerned you guys aren't.
It's 4.
Is it 4? You guys know negative times a negative is a positive?
Yeah.
Okay, negative 2 squared is 4. Make it negative. Negative 4 plus 1? Negative 4 plus 1. So when I plug in negative 2, I still end up getting negative 3. Remember, I plugged in negative 2, and so this is an example of, if I were to draw this as a mapping diagram, this is what it looks like. Still function, right? It's just one of those weird ones where you have x arrows pointing to the same number. Okay. Okay. If I plug in negative 3 for my x. Negative 3 squared. 9. Make it negative. Plus 1. Yeah, it's symmetrical. So it looks like, I should close my parenthesis there. Looks like this. Well, not quite. That's better. And it's a parabola flipped upside down because of that negative being right there in front of the x. It changed the direction the parabola opened. So that one's definitely nonlinear. So let's use maybe NL as our abbreviation for nonlinear. How about example C? Is that one going to be linear? No. right? It's got an exponent there other than 1. So let's pick some values for x and pick some values for y, and let's see what happens here. If I plug in 0 for x, what's 0 cubed? 0 times 0 times 0. Okay, so I know this function is going to go through the origin. So far, it's the only one that's gone through the origin. Let's plug in 2. What's 2 times 2 times 2? So when I plug in 2, it goes to 8. So it's all the way up, maybe there. 7's obviously the very top line, and so 8 right above that. Okay. Let's plug in -2. What's -2 times -2 times -2? I think we answered this one already. Negative times a negative times a negative, -8. And so it's going to be all the way down on this end. Now that looks like it forms a straight line. It doesn't. Okay. In fact, if I just plug in 1, you'll see that what's 1 cubed? 1 times 1 times 1. So 1, 1 is on this one. Now you can definitely tell it's not linear. What if we plug in -1? What's -1 times -1 times -1? And so it does one of these numbers. It's interesting looking. Very interesting looking. Yeah. How many times does it cross the x-axis? Just once. It could cross 3 times, but it doesn't. That's just the maximum number of times. How many times does that parabola cross the x-axis, Nuche? Twice. The exponent, so what Nuche is referencing something we talked about yesterday in Math Bowl. If you have whatever the exponent is for your x, that's the maximum number of times that your graph could cross the x-axis. So normally when we're talking about a linear function and there's just a 1 right there, it only crosses the x-axis once, it's a line. This function could cross twice. And actually it does cross it twice. This function could cross it 3 times, but it doesn't. That's just the maximum number it could. So as I start adding numbers to this, like maybe I add a x cubed plus 2x to the 3rd power minus 3x plus 6, it starts to make my little curve go like this. Like that. It adds loops to it, and that's what makes it cross more than once. You think they'd wait 3 minutes for me? No. Hello? I do. Okay, I'll send her down. Bye. All right, Caitlin, you're getting picked up for an appointment. All right. I think we're about, is this it? Is there one more? No, there's not a lot more. That's just for you. That's just for you. There's no problems here. So I've got 3 examples. The number of pounds P of carbon dioxide produced by a car is 20 times the number of gallons G of gasoline used by the car. Write and graph a function that describes the relationship between G and P. Think of G and P as being like X and Y. All right, so I'm used to having 2 variables. It looks like the G, the gallons, is my X variable. And the CO2 used, which was the P pounds of carbon dioxide, CO2, carbon dioxide. Okay, that would be the P variable, which is on the y-axis. So P is my y, G is my x, I guess is what I'm trying to say. So let's see if we can write a function from this. The number of pounds P is, so P equals 20 times G. How do I write that? Yeah, well, that's a lot easier function than what I thought it was going to be. Remember, P is the y variable, G is the x variable. What's the y-intercept of this? AJ? 0. Yeah, if I don't use any gallons of gas, I'll produce 0 pounds of carbon dioxide. It makes sense that this would go through the origin. And then the slope? What's the slope of this line? 20. Haley, you haven't paid attention one bit. close your tablet. You can sketch on your own time. This is how we fall behind. We're going to rise 20 and run 1, and then rise another 20 and run another 1, and then we end up with this linear function just with a slope of 20, just like that. That doesn't take very long. I wrote the graph, I wrote the equation, and I graphed it. That's it. Okay, next one. Instead of giving us words, they're giving us a chart, and they're asking us to do the same thing. Graph, or not graph it, just write the function. And so remember, if it's linear, I want to write it in slope-intercept form. Let's see if these are linear. Is my y decreasing by the same amount each time? What is it decreasing by each time? It's decreasing by 2. So I'm going to write -2. Because that means my run, remember my slope is rise over run. My run is -2. That's the change in the y. The rise is -2. The run is the change in x. What is the x changing by each time? It's +2. It's adding 2 each time. Okay, so my rise is -2. My run is +2. What's that make my slope? -1. Okay, so y equals -1x, or just -x. And then do they give you the x value being 0? No. If I subtract 2, I'll get to I'll skip right over 0. So instead of making it, -2/2, let's just use the reduced fraction -1/1. So let's back this one up 1. That becomes 0. Let's add this one up 1. And when x is 0, what's the y value? 1. And so my y-intercept is going to be 1. Last question. Let's start with our rise. What is the y changing by each time? Is it adding or subtracting? So it's +5. So my rise is +5. My run is, what's the x doing each time? Okay, so what's +5 over +1? 5. Okay, so my m value for this one is just 5. So y equals 5x. Do they give you the x value being 0?
Yes.
This one does. Okay, when the x is 0, what's the y?
25.
That's my y-intercept, because 0, 25 is right on the y-axis. Done. Levi, question?
I actually have a question about the first one that we did, A.
Yes.
So could we technically say that on the x input is increasing by -2?
Yeah. -2? Same as +2. You could say that. Decreasing by -2 is an interesting way of thinking about it. Okay. Now, what I have left here in your notes, this isn't homework. This is kind of like a summary of everything. Here are all the different ways so far that you can represent functions. We looked at functions where we turn, they give us words, and we wrote the equation. Obviously, you can have an equation. You can have an input-output table, a t-table. Okay? They could give you a mapping diagram. That could represent a function. A graph represents, those are all different ways that you could represent functions. And if I gave you what you're going to be expected to do on your quiz Tuesday is I'm going to give you this, 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 and this, and ask you to write the equation for each of them. So you'd say, okay, this has a slope of 1, a y-intercept of 2, it's y equals x plus 2. Or if I gave you this one, you'd say, okay, the rise is 1 each time. The run is 1 each time, so it has a slope of 1. And then the y-intercept is 2. They're all of these are that equation. Okay, those are just different ways you can represent it. And then I had this funny little comic strip on here. It's not that funny, but you've got the little dog here says, "I graphed our profits. Looks like they're increasing, right?" Until you realize it's sideways, and what's happening to their profits? Yeah, and I'm happy to say that they are going up every day. And the cat says, "You are done." Well. Something like that. Cats would be like that. You're right. All right. Take your homework. Take your restroom break. And then we'll work on homework. Don't take your homework to the bathroom. That's gross.